So ages and ages ago, scientists discovered that atoms can emit light whenever they're heated or electrically stimulated or kind of generally have energy put into them. But they only emit in certain wavelengths or certain colors. They don't give you a full range of colors, so you don't get a continuous rainbow or anything. And they also found that each element only gave off characteristic colors. So if you heated up the same atom or different samples of the same atom, you would always get the same colors. And a guy named Balmer eventually worked out an equation that could predict these wavelengths or these colors for hydrogen. And in this example, RH is the Rydberg constant, and N1 and N2 are just integers representing energy levels. And we'll get into that in a minute. So remember that energy is quantized. You can't have any random wavelength of energy being emitted, right? You're not getting a spectrum of light. You're getting these discrete colors. And this quantization explains why the n values have to be integers. If they could be any value, you could get any value of lambda out of this expression. You could get any color out of this expression. So Balmer's method kind of worked. What it implied was that if you heated or electrically stimulated or did something to the hydrogen atom, you could force electrons to move between energy levels, where N1 and N2 are just the energy levels in a hydrogen atom. So this worked to some extent. Balmer found that if you moved an electron from N1 to N2 or N2 to N1 for whatever values of N that you want, you could predict the frequencies of light that you saw in hydrogen. So you could find that these wavelengths of light could be emitted from hydrogen. But at the same time, it only really worked for hydrogen, and it had some limitations. So later, Niels Bohr expanded on Balmer's work, and he came up with some requirements. The first thing that Bohr worked out was that electrons in an atom have to orbit around that atom at certain radii with certain very specific energies, quantized systems, basically. So he imagined a nucleus with electrons orbiting around it. And those orbits had to happen at certain radii with certain specific energies. So that's the first point. The second point was that electrons in an orbit do not radiate energy. They're basically just stable there. They just stay there forever. So it's not like with planets orbiting in a sun, where eventually they're going to lose energy and they'll spiral into the sun and crash, and it's a horrible thing. Bohr said that the electrons, if they're in that orbit, they're happy there. They'll stay there and not lose any energy, and they won't spiral into the center. And the third point that he worked out, and that, to be fair, Balmer also kind of worked out, is that energy is absorbed or emitted from an atom when an electron jumps into a different orbit. And that energy is absorbed or emitted as a photon. So imagine we have a hydrogen atom with the positive nucleus and an electron in an orbit around it. So we have an electron in an orbit around it. If that jumps from a smaller, closer radius to an orbit with a much larger radius, then the electrons gained energy. It went from a lower energy system to a higher energy system. So the electron had to absorb energy. What Bohr said was that it would absorb that energy could absorb that energy as a photon. And if we write that a different way as what's called an energy level diagram, what Bohr said is a photon would come in, and the atom would absorb that photon, and that absorption of energy from the photon would cause the electron to jump. And this let Bohr work out all the energies for each orbit in a hydrogen atom. So very similar to what Balmer did. So Bohr found that the energy of a specific orbit with a specific value of n would have an energy equal to 1 over n squared times Planck's constant times the speed of light times Rydberg's constant. And this n value is labeled the principal quantum number, and each different orbit gets its own value of n. And to find the change in energy associated with an electron jumping between different orbits, you can just find the delta E. So you look at whatever energy for the orbit you start with, you compare it to the energy of the orbit that you end in, and the magnitude of that gap is just the delta E. And the expression for that is this one. And NF is the final principal quantum number, and Ni is the initial principal quantum number. As I mentioned earlier, we often represent these electron movements between orbits using an energy level diagram. So if you look at the energy level diagram I've drawn, you can see that anything that orbits with the principal quantum number of 1 are lower in energy, and each subsequent value of n represents an orbit that's higher in energy. And the energy levels, or the orbits, or energy states, or whatever you want to call them, get closer together in energy as they get higher in energy. So I'll show you a couple of small examples for energy transfers. So if you have a system where you have an electron in the n equals 1 state, that electron can be promoted to a higher energy level if the atom absorbs a photon or is heated or whatever. And at the same time, if you have an electron in a higher orbit, a higher principal quantum number energy level, that electron can lose energy and fall back to a lower energy position. So you can gain or lose energy. And there's some terminology you should know. The lowest possible energy level, the n equals 1 level, is known as the ground state. And the ground state is where you'll typically find all your electrons. In general, things like to have the lowest possible potential energy that they can. So unless you do something, things are going to be in the ground state to start off with. The other phrase you should know is excited state. And an excited or upper state is any energy state or orbit that's higher than the ground state. You don't have to have transitions between just two energy levels. You can have transitions from multiple different energy levels. So you could start with an electron in the n equals 1 state, and you could promote it to the n equals 2. And then you could promote it again to the n equals 3. And if you want, that electron could fall back down to the n equals 2 state and emit light as a photon, or it could fall all the way back down to the n equals 1. All sorts of things are possible. So you can have jumps in energy that include a difference of 1, so from the 1 to 2 energy level. You can have jumps in energy that cover 2 principal quantum numbers, or 3, or any number that you want, really. And you can also have drops in energy that happen like that as well.